So now is the time that we get to use all of the tools we've been developing so far to solve interesting problems involving variation of functions on which a functional depends. So really, we're looking for stationary points of a functional. And just to remind you, a functional is defined as follows, or the kinds of functionals that we're interested in are defined as follows. Suppose we have a coordinate plane, we have a point P, and we have a point Q, and they're connected by some function, let's call it y of x, and of course y of x, we're interested in its behavior from x equals a to b, and the corresponding point on the y-axis, y, a, and yb, but of course the function can have any behavior we want outside of that range, we're just not interested in it. But what we're trying to do is we're trying to find stationary points of a functional f of y, and that's got to be equal to the integral from a to b of some function of y, y prime, and it might have some explicit dependence on x, and integrate with respect to x. So that's the definite integral. And what this does is it takes a function y and it maps it onto a scalar f of y. And the problem is to find stationary points, or we should put that in quotation marks, stationary points, y of x, of the functional f of y. Okay, and we're going to go about this in the same way we went about solving the general n-dimensional case, by starting with our functional and making, instead of a small displacement, the language we use in calculus of variations is, well, naturally a variation. So we start with y of x and we go to, oops, please excuse me, well, yeah, of course, no, we start with y of x and we go to y of x plus alpha eta of x. And it's worth commenting on this because it's a little different to how we did it before. We always had h's as our displacements, but this time I've written it a bit funny. I've written it as alpha eta of x, and it's worth just annotating this diagram to explain what we mean. So let's say I have function eta of x like this, right? And notice I have had eta of x, so I'm going to call this eta plus of x. I've had eta plus of x vanish at both a and b, and then if I just kind of draw up here what that might look like, what alpha eta of x plus y of x might look like, what I'll get is something like this. So I might call that y of x plus alpha eta plus of x. And of course we can have any kind of displacement we like. So our displacement might look like this as well. So it could be negative, and I'm going to call this one eta minus of x. And then we're going to draw in our f of x minus, so this is y of x, plus alpha eta minus of x. So clearly we are just trying to find all of the ways to vary the function y. We're trying to find all the ways to vary the function y so that the endpoint stays the same, so that we always land on the points P and Q, right? And the way we do that is by imposing the condition that eta of x, oh sorry, of course that's eta of A has got to be equal to eta of B has got to be equal to 0. This is a function, a property that eta must satisfy. And alpha is just small, right? So we can choose it to be arbitrarily small as we would like. So after we make this displacement, f of y is going to become f of y plus, and this time we use, it's common in calculus of variations to use a lowercase Greek delta of f of y to represent the displacement in the value of the function null evaluated at some point that's displaced slightly from the stationary point. Okay. Now, the reason I'm using the language of a point is because we can actually think of this as kind of like not just one equation, but it's like an infinite number of equations indexed by the variable x. So this is kind of like uncountably infinitely many displacements. So it's kind of like uncountably infinitely many displacements. So really it's like we're solving the problem in calculus of variations is kind of like taking our work with functions to their logical limit. We started with one variable, we went to two variables, we went to arbitrarily many but still finite variables, and now we're going to uncountably infinitely many variables. So really, we're going to play the same game we played before, but just with functionals. We are going to investigate this delta y, and we're going to just be bold, and we are going to say that delta delta f of y, we're going to call that f of y plus alpha eta minus f of y vanishes to first order in our small parameter alpha, and we are going to say this is equivalent to y being a stationary point of the functional capital F of y. So now we're going to start our investigation just like we did before, but we're going to box this off as our definition, and then we're going to now investigate our variation in y that's a consequence of our of our variation in f that is a result of our variation in y. Well, we're just going to start by studying f. I'm going to start by studying f of y plus alpha eta, and this is clearly just going to be the integral from a to b of lowercase f, and looking at our definition up here, y is just going to become y plus eta, so that's going to become f of y plus eta, and y prime is going to become, oops, sorry, please excuse me, that's plus alpha eta. Y prime is going to become y prime plus alpha eta prime. Remember, alpha is a constant here. It doesn't depend on x. It's a displacement that we are allowed to choose. And of course, x just stays the same because it's the function that changes, not the point we choose to evaluate it. And that's evaluated with respect to x. To make any progress, really we're going to have to do something about that f, right? So we can use the tools we used before quite directly to get something useful out of this. So we write f of y plus alpha eta is equal and y prime plus alpha eta prime, and x, well, we just use Taylor's theorem. We use Taylor's theorem to expand this, and we get f of y, y prime, and x, but we also collect plus alpha eta df dy plus alpha eta prime df dy prime, and of course plus higher order terms than alpha squared, so terms of order alpha squared and higher. Now we are just going to investigate our functional. So looking at this, we just stick that under an integral sign to compute our functional of y plus alpha eta is going to be, well, we stick the right hand side under the integral sign, so we write the integral from a to b of f of y, y prime, and x dx, and we add in our integral from a to b, and we can pull the alpha on the outside because remember it is a constant, it doesn't depend on x, and what eta unfortunately is a function of x, so it must stay inside of the integral. The partial derivative of f with respect to y, and that's integrated with respect to x, and another term, that's alpha, again that can come out of the integral sign, integral from a to b. And as far as we know, eta prime still depends on x, so we must include that under the integral sign in the most general case. And we write partial derivative of f with respect to y prime, and we integrate that with respect to x. And of course, we must still keep our terms of higher order than alpha squared, including terms of order alpha squared. Now, we recognize this, right? This is just our functional evaluated at y. So this here is f of y. This here, we can't really do anything with this, but we would like to simplify this. So we'd like to simplify this. So we're going to give it a name. The name we're going to give it is I. We're going to give it the name I. So we're just going to investigate how we can make I a bit simpler. So we write I is equal to just the integral from a to b. So excluding alpha, we're just after the integral here. That's the eta prime, but instead of writing eta prime, I'm going to write that as d eta dx times df dy prime dx. And now you can probably see how we're going to simplify this, because this is a derivative with respect to x times something that's not differentiated with respect to x, and the integral is with respect to x. So you can probably see that to simplify this, we are completely within our rights to use the integration by parts technique to simplify this. So we write this is eta of x times df dy prime, and this has got to be evaluated from a to b. So we peel the derivative off eta, then we subtract off the integral from a to b of, and now we take the integral off eta and we stick it on to df dy prime, so that's the derivative with respect to x of df dy prime dx. So what we've done is we've evaluated this at the boundaries and we've moved the derivative off eta and onto df dy prime, and that's integration by parts. We can make it yet simpler because look at this. Remember from before, we were quite careful to define eta. So that eta of A is equal to eta of B is equal to 0. But eta's in this term. It's in this term that we're evaluating at the boundaries, but it vanishes at the boundaries. Therefore, this whole term just vanishes. We can ignore it. And that's just a consequence of us choosing eta to be an honest-to-goodness variation so that we always land on the endpoints, no matter how we vary it. And, well, we have this left over, the integral from a to b of eta d dx of df dy prime, and this is integrated with respect to x. And now, well, we can just go back to our functional, right? So our functional evaluated as our displaced point, f of y plus alpha eta, that's just going to be equal to, well, that's f of y plus alpha integral from a to b eta df dy dx, but now our newest term, integral from a to b of eta, and this is the derivative with respect to x of df dy prime, and that's with respect to x as well. And we see we can put these together because notice there's a common factor of eta in these two integrands. So we can really put them together in quite a nice way. So, of course, please forgive me for forgetting our big O of alpha squared. And this then becomes, well, f of y plus alpha, and of course I forgot my alpha here as well, integral from a to b of eta, and this is eta as a function of x. Now this is times df dy, and that came from here, but we're just collecting what's in the other bracket, what's in the other integrand over here. We're collecting this, and that's going to come as a minus, because we're collecting a minus sign, times d dx df dy prime, and that's to be integrated with respect to x. And of course, that came from here, that's that term there. And of course, the eta is just the same eta from over there, so we've collected them. Now, this is the payload. This is where we kind of get the result of all our hard work. We just move the f of y over to the other side, and we have delta f of y is just f of y plus alpha eta minus f of y, and that's just equal to, of course, I forgot my plus big O of alpha squared here. That's going to be equal to just alpha integral from a to b of eta of x times our funny expression in here, df dy minus d dx, the derivative with respect to x of the partial derivative of f with respect to y prime, all integrated with respect to x, plus higher order terms in alpha. Now, this alpha, remember, it's small, but not zero. So small, but critically not zero. And we choose alpha to be small enough for higher order terms to be negligible. Therefore, the only way for this to vanish is if for all x, this integrand vanishes, right? Because remember, eta's arbitrary. Eta is completely arbitrary just so long as it vanishes at the endpoint. If it vanishes at the endpoint, it's a good variation. We can drag its magnitude down as small as we want because it's multiplying that tiny, tiny alpha there, right? But eta is in principle arbitrary, just so long as it satisfies the boundary conditions. So because eta is arbitrary, we, it doesn't have to be zero, right? To guarantee that this is always zero, we would need for this to vanish. We need this to vanish. And that's our condition. So this is our condition, which we're going to write bright and shiny on a new page as the partial derivative of f with respect to y minus the derivative with respect to x of the partial derivative of f with respect to y prime. That's got to vanish. And this is a condition that's equivalent to the statement that y makes f of y stationary. So if y satisfies this differential equation, we say that y makes the functional capital F of y stationary. And what's also worth pointing out is this has a name. It's a differential equation. It's a differential equation, and when we solve it, we get y as a function of x, and it's called the Euler-Lagrange equation. So this is the Euler-Lagrange differential equation. Okay. It's worth also pointing out that, remember, for the 1D case, this object was just the derivative with respect to x of our function. And in the 2D case, it was another kind of derivative. It was the gradient, which was a vector valued function. And in higher dimensions, in the general case in n dimensions, we got an n-dimensional gradient. Well, really, what that tells us is that we should think of this object appearing on the left-hand side of the Euler-Lagrange equation as a kind of derivative. And we do. We give it a name. We call it the functional derivative. So we write that the functional derivative, df of y with respect to y of x, we call that the partial derivative of f with respect to y minus the total derivative of f with respect to y prime. So essentially, the Euler-Lagrange equation is just the statement that this functional derivative vanishes. And now, this is the payoff. Now we have the Euler-Lagrange equations, we can analyze any problem whatsoever where we want to make some functional stationary. So if we want to find what y of x makes some functional stationary, we just have to solve this differential equation. And next time we're going to go back to our example right from the beginning that we used to motivate the calculus of variations. We're going to bring this tool to bear on the problem of finding the function that minimizes the traversal distance between a point P and a point Q.